So in this podcast, what I want to do is to look at the problem of a heavy rod, and I'm going to assume that its weight is 50 newtons and its weight is going to act through its centre of gravity, which is in the middle of the rod, and there is going to be a force of 100 newtons acting downwards, and there is going to be a tension along this light cable which is at an angle theta, and we can work out theta in a moment because the distance between the rod hitting this wall here and the cable being attached to the wall is 1 meter, and I'm going to take the length of the rod to be 2 meters. So as well as these forces of the weight of the rod, the force applied to the end of the rod and the tension in this light cable, there will be another force which is going to be a reaction force. This presses against the wall presses back, and that force is going to be in a direction which is going to be to the right, so that it counterbalances this force to the left, or the component of that force to the left, and it's going to be at some angle, and I will call the angle phi. So what I want to do in the podcast is to find out the tension and this reaction force here. So to do that, we can draw a free body diagram of the rod, but perhaps it's sensible just to start off by calculating this angle theta, and we can do that just using trigonometry, because the tangent of theta is going to be this length divided by this length. So let's just start off by noting that the tangent of theta is 1 meter divided by 2 meters, so that's a half. So therefore theta is the arctangent, the inverse tangent of 1/2, and if you put that into a calculator, what you are going to get is 26.57 degrees, assuming that your calculator is set up in degrees. So that is the angle. So what I want to do now on the next slide is to redraw this, or be more explicit, to draw a free body diagram of the forces acting upon the rod. So what I've done on this slide is I've drawn the free body diagram. Here is the rod. Its weight acts through the middle of the rod, through the centre of mass, and there is an external force of 100 newtons acting at the end. We have the tension along the light cable at the angle we've just calculated. We have the reaction force F off the wall at an angle that we don't yet know, and I've also drawn here Cartesian coordinates, and if we remember that this is 2 meters long, the distance from here to here is 1 meter, and the distance from here to here is 1 meter. And the other thing that I've written out is that in equilibrium, the sum of the forces on the rod are going to vanish, so this plus this plus this plus this as vectors must vanish, and also the sum of moments of forces must vanish, so we can be looking at, say, the moments around here, or the moments around here, or the moments around here. And what I'm going to do is I'm going to give these points names, and I'm going to say that this is point A, this is point B, and this is point C. Now, what I want to do first is to calculate the tension. I know the angle, but I want to calculate its numerical value, and I think the easiest way to do that is to take moments about the point A. So about A, the reaction force is not going to have a moment because its line of action is straight through A. So its perpendicular distance to A is 0. So the force times 0 gives 0 moment. This force will have a moment about A. It's going to be this distance times that force, because this is a right angle. and then again here, this distance times this force for the moment of the force of 100 newtons. What about here, the tension? Well, we can divide the tension into a component acting that way and a component acting this way. The component acting horizontally will have no moment because its line of action is straight through A, and the component acting upwards, because it's acting perpendicularly to this line, will have a moment which is this distance times the size of the force. And in everything I've said up to now, I've not been too careful yet about the signs of the moments. I'll look at that in a moment. No pun intended. Okay, so let's take moments about A. And the thing to realize is that we have a sign convention that forces that would try to make the object, in this case the rod, rotate in an anti-clockwise direction about A are going to have a positive moment of force, whereas this force and this, which would try to make the rod rotate in a clockwise direction, have negative moments of force. So the negative components first, we have minus 1 meter times 50 newtons minus 2 meters, because that is the total distance, times 100 newtons. And then we add the positive component from here. So the distance is again 2 meters. And then it's going to be the component of t that acts vertically upwards, and I'm going to call that t sub y. So it's times t sub y, and this has to equal 0. And this is the equation that is going to tell us what this component is. Now let's just draw a quick diagram for this force and see how things work. So this is, let's say, t, its overall size. This is the angle theta that we know, and we can decompose t into a component acting this way, t sub x, and a component acting upwards, t sub y. And this length and this length are the same, so I can just draw here t sub y. So we see that t sub y is t times the sine of the angle theta. To put that differently, the sine of the angle theta is this over this, t sub y over t. So t sub y is t times sine theta. So therefore we can rewrite this entire equation, and I'm going to take these two terms which are negative over to this side as I do it. So what do we have? Let's look at this first. So it's 2 meters, I'll put the units at the end, times ty. So it's 2ty, but ty is t sine theta. So we have 2 t sine theta is equal to, and now we've taken these to the other side, it's minus 50 Newton meters minus 200 Newton meters, so it's minus, but now we've taken it over to the other side, it becomes positive, so it's plus 250 Newton meters. So we know what theta is, we can substitute this in, and what we are going to find, if we do that, is that t is 279.5 newtons. The units of meters have cancelled. Remember, this is 2 meters. And so to say two significant figures, T is 280 newtons. So that's our answer for that, and remember we know the angle already. And if we want to write T as a vector, well, T as a vector is going to be T sub x times I, but it's acting this way, so it's going to have a minus sign. And then T sub x is going to be T, which we have here, or more accurately here, times the cosine of theta that we've worked out, and we can put that into a calculator, and what we should find, and I very much encourage you to check this, is that we get minus 250 I newtons, and in the j direction it's acting upwards 125 in the j direction newtons, and that is our answer for the tension expressed in terms of components of the vectors, and this together with the angle is expressing the force in terms of a magnitude and a direction. So what I want to do now is just talk about how we could have taken moments about A in a very slightly different way as an aside before we go on to calculating F. So as an aside, we've just calculated the moment of the tension about the point A by breaking this force up into components, but a different way of doing it would be, we know the direction of the tension force, remember we've calculated the angle theta, and we just need to work out the perpendicular distance. So what I'm going to do is I'm just going to drop a perpendicular line here. So this is at right angles, and this distance is d, which we can work out from trigonometry. The length of the rod, remember, is 2 meters, and what we can do is again calculate the moment of T about A, the point A, around here, by saying that it's going to be the size of the force times this distance, and again this is a physical object, so the way we calculate it shouldn't matter, we must get the same result, so check you get the same result. So that's a small exercise for you, and now let's go back and we're going to work out what the reaction force at A from the wall is. So on this slide what I want to do is to calculate the force from the wall, the reaction force, and it's a vector and it's going to have two components, as you can see here. And I could say, well, let me take moments about here, for example, and this is then going to have a negative moment about C, and it will be balanced by this force having a positive moment about C, and the tension and the force applied at C have no moments about C because they act through the point. But the trouble is that we want to have both components of this force, and that's only going to give us an equation for one. So I think it's easier just to say, let's work out the components of the forces acting upwards and the components of the forces acting sideways, and that will give us two equations for the two unknowns in our vector F. So let's start off by writing down these two equations. So what we're going to demand is the sum of the forces acting on the rod must vanish. And writing this now in terms of components of vectors, we have in the I direction part of this force and part of this force. So we're going to get I times F, the magnitude of this force, times the cosine of the angle phi, minus T, the tension in the light cable, multiplied by the cosine of the angle theta, and then we're going to have in the vertical direction J, upwards, F sine phi plus T sine theta, and then we're going to subtract this force and this force because they're both acting straight downwards, so that's 50 newtons and 100 newtons, so it's minus 150 newtons, and that's going to have to vanish, and it's a vector, so I mean that both components are going to vanish. So we have two equations for the two unknowns. Remember, we know what the tension is and we know what the angle theta is. So our unknowns are F and F theta. A different way of writing this would be to say that we have I, and then using what I hope is somewhat obvious notation, Fx, the component of this in the x direction, because that's what this means, minus t cos theta plus j, and in the j direction it's fy, plus t sine theta minus 150 is equal to 0. So this is two equivalent ways of writing the same thing. So when I solve it now, what I'm going to do is I'm going to use this version here. So what we have is fx is equal to t cos theta, and that comes from demanding that this component of the overall vector of all the forces vanishes. And we're also going to have Fy, the vertical part of this force, this reaction force F acting on the rod, is going to be, and now this vanishes, so I take this to the other side, it becomes positive, to this to the other side it's negative, so we're going to have 150 minus t sine theta. So just to think about what these two equations here are telling us, so this one is saying that the vertically upwards part of this force is equal to the forces acting downwards with the contribution upwards from the tension subtracted. And this equation is saying that the force from this in this direction is equal and opposite to the force from the tension in this direction. Now we know what theta is, and we know what t is, so we're in a position to work out what these two components are. So I encourage you to check, but what you're going to see if you put these numbers that we have into a calculator is that Fx is 250 newtons and Fy then is 25 newtons. So the overall reaction force is going to be 250 I plus 25 J newtons. So that's our answer for this force in Cartesian coordinates. So if we want to work out now what the force is in terms of a magnitude and an angle, The simplest thing to do is to draw a diagram. So this is the rod. We've also got the force acting this way at our angle phi, and this force is built up out of two components. So the one component is 250 newtons this way, and the other component, not to scale, is 25 newtons acting upwards, and the magnitude of the force is the length of the hypotenuse. So F, the magnitude of this reaction force, by Pythagoras' theorem, is the square root of 250 squared plus 25 squared. And from that, using a calculator, what we obtain is, sorry, I shouldn't have put a vector sign there. What we obtain is that the magnitude F is equal to 251 newtons to 3 significant figures. So it's very close to 250 newtons, and that makes sense if you look at that, because this is much larger than that. And the tangent of phi is that over that, so therefore we have that phi is the inverse tangent or arctangent of 25 over 250, so that's the arctangent of 1/10, and what one obtains in degrees is that this is 5.7 degrees. And again, that makes sense. If you look at these numbers here, you can see that the angle must be quite small, and we get indeed a small answer. So what we've got here is we've worked out the reaction force, and we've written it in two different ways, once in terms of Cartesian coordinates and once in terms of its magnitude and the direction. So those two answers are equivalent. And if you want to do a partial check of our result here, one thing you could do would be to say, well, imagine we were to take moments about C. This force and this force would not have a moment about C because their lines of action go through the point. This force has a moment about C, and the force is acting perpendicularly to this line, and the distance is 1 meter, so the moment of this is going to be 50 times 1, and it's positive, so that's got a moment of 50 Newton meters about C. And if we consider this force, it's 2 meters away from C, and its component in the x direction has no moment about C, but its component in the y direction does, so we're going to have that the component in the y direction times 2 is equal to 50 times 1, and the component that we obtained in the y direction here is 25 newtons, and 25 times 2 is equal to 50 times 1. So that makes perfect sense and gives us confidence in our results. And if you'd like to do another check, you are very welcome to take moments about another point, such as here, but I'm going to stop this video here.